name is AIDAN matrix number F25A1836, and I am from the SFM program. I am the developer behind the Sustainable Food Security Modeling Initiative. This project bridges data science, calculus, and precision agriculture to optimize crop management in Malaysia. So that is all for my self-introduction. Now I'm going to go into the summary of the chosen bioscience problem. This project addresses the challenges of optimizing the harvesting time for Malaysian oil palm or fresh fruit branches, where after pollination, the fruit bunch grows in a biological sigmoid curve over roughly 20 weeks. You can see over here. The problem is figuring out the exact biological peak before the fruit overripens and drops, which compromises crude palm oil quality. And to solve this, I developed this app which uses calculus. It models the fruit's total weight over time and uses its first derivative to pinpoint the exact week where growth velocity is at its maximum. So for the importance of studying this bioscience problem is for national food and economic security, where palm oil is a staple agricultural export and global food asset, and maximizing it yields efficiency, directly secures supply chains. And second is for sustainability, where reducing agricultural waste by preventing the spoilage of overripe fruits while ensuring that the highest quality of crude palm oil is extracted per tree. So before we go into the chart, we will see the sigmoid growth function, where it is the model of the total weight of the fruit bunch over week, which is calculated by X, where, as you can see over here, the sigmoid growth function is 25, which is the carrying capacity. 0.4 is the growth rate coefficient under optimal Malaysian climate conditions, and 10 is the inflection point or the week of peak growth rate. And for the derivative, it calculates the instantaneous weight gain velocity or kilogram per week using the chain rule, where in precision agriculture, this derivative eliminates guesswork by showing exactly how fast the plant is synthesizing biomass at any given moment. So now I'm going to explain the chart. So in the first week, the bunch weight is 0.665 and the growth velocity is 0.259. And at its peak, which is week 10, the bunch weight is 12.5 and the growth velocity is 2.5, and it only starts to go down after that. So week 10 is the peak. So at week 10, the fruit bunch is hitting its absolute peak speed of development, and it is gaining 2.5 kilograms of mass per week. This is the optimal metabolic inflection point where we should plant our harvesting teams immediately. For my final point, which is how do I make this HTML better or to improve the user experience, I would recommend adding dynamic input sliders for the model parameters, which you might ask why. For right now, the carrying capacity and the growth rate and inflection point are hard-coded into your JavaScript and math formula. However, real-world biological data changes due to seasonal droughts, pest infestations, or variations in fertilizer. Now, how do I implement this? I have to add a HTML range which inputs allowing users to slide and alter these variables and link them to update your charts dynamically, which allows us to update the chart in real time. That is all from me. Thank you.
Everyone, my name is FUDHAIL HADI bin IDRUS and my metric number is F25A1957, and today I am excited to present my project, the biocalculus analysis of Malaysian Tenera oil palm seedlings. I choose this bioscience problem because Tenera is the most important oil palm variety in Malaysia. The problem we face in the agriculture industry is timing. Every year, the thousands of the seedlings are lost because they are transplanted into the field at the wrong age. If we move them too early or too late, the growth is stunted, and it costs the industry millions of ringgit. And why studying is important? It is because we need a precision agriculture by using mathematical models. We move away by guessing and towards data-driven decision. Studying this growth curve allow a plantation manages to predict exactly head at any month. Understand the growth velocity so they can apply fertilizer at the exact moment when the plant's metabolism is at this peak. Basically, we are using calculus to ensure every single seedlings survive and thrive. As you can see on my website, I have a slider here. When I move it, look how that when I move it, look how data on my website change in a real time. Point to the math box on the right. We have our mathematic models is our position function. It shows the total height. The first derivative is it show the instantaneous growth rate. This is the most important part because it tells us the speed of growth. Show a status. Notice that when I slide to 12 month, the status change from nursery to field ready. This visual aid helps a non-technical worker understand that it's time for transplanting. Future improvement and closing. To conclude, this project bridges the gap between biology and technology. However, there is always room for improvement. One way to make this HTML better is to integrate real-time with the data. If you could connect this to a with the API. The growth model could automatically adjust the formula based on local rainfall and temperature, making the prediction even more accurate. That's all from me. Let's make agriculture smarter with code. Thank you.
Hi, my name is Wan Alif Asyraf and my matching number is F25A 1991. Today, I will present my bioscience project on estimating glucose content in fruit juice using mathematical modeling. This project combines bioscience and mathematics to study the concentration of glucose in fruit-based products. The purpose of this project is to accurately predict glucose level and help improve quality control in food product. Following the introduction, this project focus the problem of estimating glucose content in fruit juice. Glucose is an important sugar that affect the taste, quality, and nutrition value of fruit-based product. However, determining glucose content accurately can be challenging because fruit contain complex biological component. Therefore, mathematical modeling can be used to estimate glucose concentration more efficiently and accurately. This problem is important for several reasons. This bioscience problem is important because glucose content affect the taste, nutritional value, and quality of fruit juice. By studying glucose concentration, producer and ensure that their product meet quality standard and provide better product for consumer. In addition, this study can also help research develop more efficient method for food analysis. There are two mathematical model to find weight accumulation and instantaneous growth rates. For the first one is logistic growth model. FX calculate the total mass of the fruits in gram based on the number of wheat after flour induction rather than assuming a constant speed. This formula generate an S-shaped curve that mirror natural biological development. Growth begins slowly during early cellular formation, shoot upward during a rapid middle stage spurt, and eventually flattens out as a fruit mature as caps at its maximum potential weight L, and with the curve steepness controlled by the growth constant K. Second is first derivative fx shift the focus from total weight to real time speed, measuring the instantaneous growth rate in gram per weight, represented as a bell-shaped curve. This formula calculates exactly how much weight the pineapple is packing on at any specific moment. It shows that the speed of weight giant start low, accelerate to its absolute peak at the mind point, inflection with x0, and then steadily decline back towards zero as the fruit finishing ripening. Next, for the result, let's look into the graph curve for the first week 0. The staining growth is 5.8 and the cumulative fruit weight is 14.7. In the middle week, which is week 12, the cumulative fruit weight is 900.0, and for instantaneous growth rate is 118.0. For the week 22, which is the last week in this graph, show that cumulative fruit weight highest among the past few weeks. Score show that week point is 1767.6, and instantaneous growth rate point is 12.7. In conclusion, suggestion to improve this page is add a dynamic tangent line using JavaScript. This feature will show a straight line on the graph to explain the slope more clearly. That's all for me. Thank you.
Good day, everyone. My name is NURSYASYA BINTI FARIZOL. My number matrix is F25A2009. Today, I will present my research project titled Food Security and the problem I am focusing on is how to maximize rice yields for the MR297 variety. In Malaysia, rice production is very important for our food supply. To get the best yields, farmers must apply fertilizer at the perfect time. This is when the plant is growing the fastest. Right now, finding this exact date manually is very hard. Okay. Why is this study is very important. First, it helps to support our national food security. Second, it gives farmers a clear guideline or schedule for so they do not waste fertilizer. To solve this, I use a maths model. The H2 equation. This calculate the total cumulative height of the paddy over its 100 to 120 days or cycle. The H primer, the H primer to the equation. This is the first derivative. We use this to find the exact growth speed of the plant per day. The interactive. The green line show the paddy head, and the orange line show how fast its growth. Our project show that 55 is the most critical day. On this day, the paddy head is 50 centimeter, and the growth speed is at its maximum value, which is 2.2 to 20 centimeter per day. This tells the farmer is the perfect time to apply fertilizer. Finally, to make this HTML website better, we can add a download report button. This will allow farmers or officials to download the DAP schedule as a PDF file directly to their phone. In conclusion, combining math and bioscience can help farmers optimize their crops and protect our food security. Okay, that is all from me. Thank you.